friends, today we are going to see energy harvesting methods through piezoelectricity and thermoelectricity. First of all, what do you mean by piezoelectric sensors? The sensors which work on piezoelectricity is known as piezoelectric sensors. So piezo, which is a Greek term signifying press or skews. So here the energy harvesting source, vibration, heat, light and radio frequency, and we are going to see the harvested power from these different sources. From the vibration, the efficiency goes up to 50%. The human 4 microwatts per centimeter square. If you are using in industry, the harvested power is 100 microwatts per centimeter square. If the source is heat, the efficiency varies up to 10%. For the human, 30 microwatts per centimeter square. Industrial, 1 to 10 milliwatts per centimeter square. If the source is light, the efficiency is up to 40%. For the indoor, 10 microwatts per centimeter square. For the outdoor, the harvested power is 10 milliwatts per centimeter square. For the radio frequency, the efficiency varies up to 50%. For the GSM, the harvested power is 0.1 microwatts per centimeter square. For the Wi-Fi, the harvested power is 1 microwatt per centimeter square. So piezoelectricity. So it is also called the piezoelectric effect. In the presence of an electrical potential across the sides of a crystal, when the mechanical stress is applied by pressing or squeezing it. Here, the piezoelectric material is placed above the structural support, and this is the additional mass. So the effect is piezoelectric or capacitive or electromagnetic. So these are the mechanisms where the piezoelectric sensors work. Piezoelectric, the strain in piezoelectric material causes a charge separation. Voltage across the capacitor involves. This is the capacitive effect. The changes in capacitance causes either voltage or the charge increase. The electromagnetic effect, the relative motion of a magnetic mass causes the current in a coil. So in short, piezoelectricity or piezoelectric effect is the presence of an electric potential across the sides of a crystal when mechanical stress is applied by squeezing it. The crystal acts like a tiny battery with a positive charge on one face and the negative charge on the opposite face. So this is the piezoelectric effect, which is discovered by Jacques and Pierre Curie in 1880 in the effect of pressure on the generation of electrical charge by the crystals. So direct piezoelectric effect, when the pressure is applied or when we apply or pressure or vibration in the crystal, the liberation of positive and negative charges will be there. Due to the charge separation, there will be flow of current in the crystals. So this is called piezoelectric effect. The effect is reversible. So that is converse piezoelectric effect. Whenever an electric field is applied onto crystal terminals, it undergoes mechanical stress and results in shape change. This is known as inverse piezoelectric effect or converse piezoelectric effect. Examples: piezo buses, quartz watch, etc. Piezoelectric conversion. When a sensor works on the principle of piezoelectricity, where electricity is generated if mechanical stress is applied to a material, a sensor that implies the piezoelectric effect to measure variations in acceleration, strain, pressure and force by converting them into electrical charge that is named as piezoelectric sensor. Here D is electric displacement, which is equal to dt plus epsilon E, where D is electric displacement in coulombs per meter square, small d is piezoelectric coefficient, capital T is stress, epsilon is permittivity, and capital E is electric field. So piezoelectric materials involved are rochelle salt. This was the first material discovered to exhibit piezoelectricity. Baking soda plus cream of tartar, which is piezoelectric crystals. The baking soda is nothing but sodium bicarbonate. Cream of tartar here used as potassium bitartrate. Piezoelectric crystals used as potassium sodium tartrate. The crystals are quartz, cane sugar, and rochelle salt. Ceramics, lead zirconate titanate, barium titanate, polymers, polyvinyl leaden fluoride. These are the piezoelectric materials used in piezoelectric sensor. Applications, it can be used as an actuator where electrical energy is converted into mechanical energy. Examples, piezoelectric buzzer as already said, nano positioning, piezo inkjet printer. And then power source, so which is mechanical to electrical. Examples, grill lighter, energy harvesting, paper-based piezo-resistive force sensor. So in a piezoelectric crystal, the charges are exactly balanced in unsymmetrical arrangement also. The effect of the charges cancel out each other and hence no net charge will be found on the crystal faces. So when the crystal is fused, the charge in the crystal becomes unbalanced. Hence from now, the effect of charge does not cancel with each other, which make net positive and negative charge to appear on the opposite faces of the crystal. By squeezing the crystal, voltage is produced across the opposite side, and this is the piezoelectricity. So piezoelectric lighter. So here a small spring powered hammer rises off the surface on the piezoelectric crystal, which strikes the crystal as the gas is turned on. This impact creates a large voltage across the crystal and therefore a spark between the wires which ignite the gas. So here mechanical shock is converted into electricity. Next, piezoelectric buzzer. So the piezoelectric diaphragm consists of a piezoelectric ceramic plate which has the electrodes on both the sides and a metal plate. So here when the AC voltage is applied across the electrodes, the bending is repeated, producing sound waves in the air. In many applications like car reverse indicator, computers, etc., buzzers are used. A certain amount of voltage with a value of magnitude and frequency is applied on the crystal, which makes the crystal to vibrate. The vibration here is converted into sound. So this is about the piezoelectric buzzer. Then atomic force microscope. So here also a photodiode and laser is placed on the surface. So after the vibration from the piezoelectric scanner, image is viewed on the detector and feedback node. So then we can see a van der Waals force from the CRO. So this is the heat transduction mechanism, that is from thermoelectricity. Thermoelectric, here the direct conversion of temperature differences to electric voltage and vice versa. Seebeck effect and Peltier effect. Heat engine system that performs the conversion of heat or thermal energy to mechanical work. So Thomas John Seebeck is discovered the thermoelectric effect in 1921. See, the direct conversion of temperature difference to electric voltage and vice versa is shown here. Module contains n-doped and p-doped semiconductor material connected electrically in series and thermally in parallel. Charge carrier is diffused due to temperature difference and the motion of charge carrier result in a current flow. Figure of merit is given by Zt is equal to S squared sigma by K into T. So this is the Seebeck coefficient and sigma is the electrical conductivity, K is the thermal conductivity. So these we measure our average values. It can vary with nanoparticle size, shape and density, vary with superlattice period, flatness and grain size, vary with alloy composition. So these are the figure of merit was less than 1 for a long time. Then it can changes with the temperature difference for the different materials. Heat sources, industrial process, automotive, aviation, solar thermal, living space and human body. Thank you.